How to model different types of cooling. Let's look at different data center cooling models. This room has traditional downflow cooling. In it, large cooling units send cold air under a raised floor. The cold air then comes out through perforated floor tiles. Let's add more perforated tiles. Capture index and temperature are recalculated immediately. We can also turn on more detail to see under the raised floor. I'm enabling additional overlays specific for downflow cooling. Floor plenum overlay calculates speed and volume of air movement. This is the air pressure in the plenum. Now, let's look at this room in 3D view. We can see perforated tiles and raised floor plenum. Let's calculate the temperature map. The temperature map is calculated on client computer. Once it's calculated, I can position the cooling plane anywhere in the room. I can also look at the velocity plane. I can see how the air comes out of the perforated tiles and how it's sucked into coolers. I can center the view on a particular piece of equipment. Now, the view will rotate around this item. Note that the 3D calculations are based on the nameplate values. And that's how you model downflow cooling. Now, let's look at in-row cooling. In this room, cooling units are positioned in the rows. I can get load and temperature values for the cooling units. For each rack, I can get the temperature and capture index. I can also simulate the switching off of a cooling unit, and then see the results immediately. Let's look at this room in 3D. This cooling type does not require a raised floor. Also, it's quicker to calculate a temperature map for this model. The walkway seems to be rather hot, but the rows are properly cooled. This room looks very empty. I can add some room fixtures to add as a navigation aid. I can add a door to the room and a window. I can also define the size and position of these fixtures. The doors and windows will appear in the 3D view, but they do not affect the calculations. They are presumed to be fully insulated. And that's how you model in-row cooling. Now let's take a look at another cooling model, over-aisle cooling. In this room, cooling units are placed above the hot aisles. To capture the hot air expelled by the equipment below. This model requires a hot aisle containment system. You then need to drag overhead coolers on top. The containment system keeps hot air away from the rest of the room. Now, let's look at this in 3D. We presume that hacks have a room between the coolers. It takes longer to calculate this model's temperature map. But the entire room outside the hacks should have the same temperature. Let's change the temperature scale. Now I can see some hot air inside hacks. The doors are presumed to be well insulated. We can see more hot air spots. Let's look at the velocity plane. Here, the colors represent air velocity, not temperature. I can see how air is expelled by coolers and sucked back by the racks. The last model is EcoBreeze cooling. In this example, there are no coolers in the room. They're placed outside the building. We model this by placing ventilation grills on the walls. They move air in and out of the room. In and out airflow must be balanced. For this reason, I'll add another grill with air coming into the room. It's positioned just above the floor. Let's look at it in 3D. Air is expelled through grills above the drop ceiling. In this way, cold air is brought into the cold aisle. Let's calculate the temperature map. I can see hot air rising to the ceiling. You can change the temperature map colors. For example, you can use more traditional infracam colors. Now, let's look at the velocity plane. I can see air flowing into the room. The air eventually diffuses through the drop ceiling. And that's how you model different types of cooling.